Okay, so we have found the right presentation. So I want to welcome Shahin Asghari. He is a research fellow from Professor Annette Mütze from Graz Technical University. And you are at this institute from Professor Mütze since more or less 1 year. And today he will give us a presentation about concept of PCB motor for fan application with Ferrite core. Welcome and have a good presentation.
Thanks to Michaelis. Hi, everyone. My name is Shahin Asghari, and as you can see, I am with the Christian Doppler Laboratory for brushless DC-derived fan and pump. So, and also with Electrical Derived Machines Institute in Graz University of Technology. We are cooperates with MSG Mechatronics. It's a company that they made small drives like fans, actuator, and some small pumps for automotive applications. So as you can see, the title of my present, it's just a concept for PCB motor with Ferrite core. Here is the table of contents of my presentation. I start with introduction, very, very brief introduction to our application. We name it sub-fractional horsepower motors, and define the problems and solution challenged in this kind of applications. We go through these air core PCB motors. It's not new. It's new in the recent years, but we just want to tell something about this air core PCB, and then we propose this PCB motor with core. We have some challenge for designing and producing the axial flux motor, so we go through it. We propose the material that we want to use in this application. It's mostly Ferrite. After that, there are simulation results and some possibility for future. So, if I want to say some brief thing about the sub-fractional horsepower motor, they are mostly less than 2 or 1 watts. They are very, very small. The primary design criteria is different with this. All of the presentation that you listen to this in recent day, it's not efficiency, it's just the cost. So the first thing that we should do is reducing the cost. And our main goal is that to reducing the cost. There is another sub-optimal behavior. So most of our fans that we are using now in this MSG Mechatronics, it's one-phase motors. They have a fluctuating power and torque, very high torque grips. They have high cogging torque because of the slot pole combinations, and high torque grips, as you say, it's one-phase motor, and a result of this high torque and high cogging torque is high noise and vibration inside the motor. So every day they want to reduce this noise, especially in automotive applications. Some of this application for inside the automobiles or cars, it's like cooling fans, small actuator inside the motor for cooling headlights, for example. And in the right side, you can see a small fans, radial fans they are producing now. And in the bottom of this picture, it's the two single phase sub-fractional motor. The right one is a claw pole machine, and the left one is radial flux. So these are, the right one is presented by our previous colleague, Dr. Stefan Leitner. And he did a lot of work to reducing the noise of this kind of machine. So what's the problem? As I say, says before, that's the cost. It's main our problem. Noise, it's the second one. And we have some solution for solving this in this application. For example, when you want to reduce the cost, you can reduce the complexity of the motor, reduce this number of the components, and avoiding using the NDFEB magnets, because you know every day the price of NDFEB increases. So we want to use, for example, another magnet that's for many years people use this in this kind of magnet inside the motor, the Ferrite magnets. They are very weaker than NDFEB, but we think that for this small application, we don't need to very strong magnets. And there is another solution for cognitive reduction. We could use a pole slot combination. Use 3-phase instead of 1-phase for torque ripple reduction, and use the new structure for our purpose. Here is the one common PCB starter motor or air core PCB motor. It's produced by e-circuit motor. They are very professional to making this kind of motor. It's easily for every size. They had a very high quality PCB for this design. So as you can see in this slide, high flexibility for a starter design, very small and very big. It's possible. It's easily scalable. There is no iron inside the core, so there is no cogging torque because no reluctance changed in the air gap. And you can integrate it with electronic parts, so it's another reason that you can reduce the price. And it's axial flux, so it's like other axial flux, it needs lower space requirements in axial direction. In the picture, you can see some one of our design that I told you. It's designed by Dr. Stefan Leichner, our previous colleague. It's air core, seems like that previous slide that I showed you, but it's designed for a small application and for a small fan application. As the result, we have some disadvantage for this design. The torque density for this design is very low. As you know, when you increase the thickness of the PCB, your air gap increases. And another issue that we have to produce sufficient flux inside the air gap, we should use a strong magnet, but we don't want to use it because it's expensive. And the other challenge is that the higher ohmic resistance inside PCB, because there's no winding here, just a trace for PCB, and that's it. No winding. So the total resistance is relative to higher, relative to common structure. What is our proposed motor? We want to use core like any axial flux motor with the PCB. So we use PCB as a stator and winding, a core, the axial core for our starter, and the magnets. At the end, we can use a back iron or no, but our preference is that I explained to you in the next slide that we don't want to use back iron. The magnet that we prefer to use comes from Schoenberg company. It's the NDFEB with residual luminance around 0.275 Tesla. So you can see that it's 2 weeks. We try to place a lot of pole, 14 pole pairs or 28 poles to better use than the stator part and reduce the material. But there is a problem for this kind of design. Your frequency should be increased. As you can see, it's around 1000 hertz. So it's the problem for ion and the ion losses. Here is a sample of a stator for axial flux motor. Everyone knows about the challenge of this kind of the motor, especially when you want to use lamination with the axial flux. It's very difficult, it's expensive. And if you want to go to some SMC material, it's good, but for this application, it's expensive. So we don't want to use the SMC. And the other important thing is that because we use very, very weak magnets, our flux density is not that much that we need to some kind of SMC, and we pay a lot of money for this kind of core. Our proposed material use the Ferrite core that's mostly used for a power transformer in electronic device. So you can see the BH curve of this material. The saturation point is around 400 millitesla. And the good news for us is that if you look at the right picture, it shows the losses relating to frequency in two different temperatures. You can see at the frequency that we want to work around 1000, 2000, the losses is not at least defined, and it's very, very low, very, very low losses in this frequency. So we can easily use this material. Here you can see our models. I just want to mention some experience with using the JMAC. We use previous version 18. So because it's an axial flux and there is some ununiform air gap. So before with 18 version, you should use generate mesh at each step to generate mesh. But good news that with new version, we use 20. So this problem is solved and you can use a slide meshing. So your simulation will be a little bit faster. And we use a layer of air just between, we defined a layer of air between the air gap and use mesh tools and mesh parts definition to concentrate our focus in the area that's the torque and the magnetic flux has happened. So it's our experience. Maybe it's useful for someone. Okay, here is the contour of flux density in the our core and magnets and back ion. As I said to you before, you can see the flux density in our teeth. It's around 0.3 Tesla. So we don't need to use iron or I don't know SMC material for this very low flux density. And we try to keep it around 0.3 Tesla because it's the knee points of the Ferrites. And you can see after this amounts, the permeability is decreased. So we try to keep our design in this area. Here is our configuration bindings. So we designed a PCB for this application. It has 8 layers. You can increase the layers up to 28. Your air gap distance doesn't affect because you have a core inside your motors, and it's not fully optimized as our results in simulation shows most of our losses comes from this part because our coil is inside of this PCB. And if you can reduce the resistance and some other losses inside this PCB, you can easily increase your efficiency. But it's the next step. Just to know, we want to introduce the concept. Okay. Here is no load analysis from the JMax software. In the right hand is by EMF analysis. It's almost sinusoidal because we use fractional slot pole combination. And in the left hand, it's very important for us. It's the cogging torque. It's peak to peak. It's around 0.2 millinewton meters. So it's the torques that produce vibration mostly and some acoustic noise inside the motor. Here you can see the load analysis of my presentation, our proposed motor. You can see the average output torque is around 3 millinewton meter. So the RIP is less than 3 or 3.5% of output torque. It's very, very low for this small application. For have a fair comparison, here is one of these single phase motors that commonly we use. You can see that's the fluctuating for or ripple of the torque is 100%. It's a start from 0 going to up and come down. So it's made very, very high vibration in the, especially in the lower speed. That it's not a good idea for lower speed because our new application is a lower speed fan inside this ventilating seat. So it needs to lower speed and it's make a lot of vibration. And in the left hand is a phase current, so it has a lot of harmony. Our proposed structure, you can see the result again. The ripple is very low. We know that we excite a machine with sinusoidal excitation, but maybe it's not that good in the application, but we at least it's very, very lower than 100%. So we think it's a good idea. And for the additional design possibility, we're thinking that use eliminates the back ion, removing the back ions, because if we do it, we can make the rotor with fan shafts and all of parts with one injection molded. So it's just one injection, and the fan magnets and all of parts it produces. It's reduced the complexity of the motor procedure for mass production. It's reduced the price a lot of. It's very cheap. And for next step, at the moment, because we work in the automotive application, so our voltage limited in 12 volts, but most of our problem here is the resistance for the PCB. So if we could use a better PCB or thicker trays and reduce this resistance and optimize the PCB, we can go for higher speed because the losses from the core is nothing, and we can go for higher speeds and increase the efficiency, but it's the next step. And for the conclusion, I can say that after the simulation shows that it's feasible that we do it. If we can do it, there is just 3 parts: a stator, PCB with all of electronic parts, and the rotor. So it's just 3 pieces. And for the mass production, it's reduced a lot of cost and investment. For example, if you want to invest for a winding machine, You don't need to winding machine in this processor, and just easier to produce this kind of motor. Thank you for your attention.
Thank you to you, Shaheen, for your presentation. And so to the audience, are there any questions from your side? Bernd?
Thank you for this nice presentations. We have investigated about this topic about several years ago in some student projects, and we came up with a solution that's maybe interesting or not for you. I don't know about the cost, but at the end we have used SMT components for the coils because they are very cheap and high volume number. Instead of making the coils directly in the PCB, you can use surface mount devices, ready-made ferrite coils. They can be bought in different shapes, and they have already a pull shape and are quite easy to mount, and yeah, it's very easy design, and you have a very high fill factor.
Yes.
You don't need the copper trays anymore, so maybe that's also a solution to look at.
Yes, thank you. Thank you.
Another question from your side? No, it seems was
Thank you.
holistic. Thank you very much again for this very nice presentation.